So we are still in the early stages, but by far ahead from the rest of the competition, which we would talk about. But in this lecture, I hope to leave you guys with tools, technologies, applications of TinyML and how disruptive it can be to several markets and verticals. And it's just imagination is the limit. So with that, here is the agenda, right? So I would start with application and use cases, and I'll go over a couple of them very briefly. Would leave you with some references to look later on if it keeps you excited enough. And then we'll talk about framework tools and techniques later in the talk, and briefly about algorithms and optimizations. And then I plan to keep it interactive. Like I said, my whole idea is to leave you guys with a little bit of an excitement. And so that being the primary focus, if you have a question, please do ask. Unmute your mic, go ahead, ask the question, interrupt me as much as you would like, because that is my primary focus. With that, let's move on. So what is ML in TinyML, right? And most of you guys must have heard about ML, and this Venn diagram on the left is kind of cliche at this point. Has been so AI, deep learning is part of machine learning, and machine learning is part of artificial intelligence. And so ML and TinyML is essentially bringing machine learning to tiny devices. And the hardware point of view, those are called tiny devices, IoTs, edge devices, or MCUs. MCU is the hardware component. If you have a GDRS module or a Wi-Fi module, then it kind of becomes an IoT, if you want to call it that way, or edge device. Edge devices typically are called without power limitations. So there is a boundary between edge devices, IoT devices, MCU devices that is kind of hazed at this point. But we would, whenever I say one, I mean the other three as well. And the other terminology that we will use in this is network, cloud versus edge. Cloud, as you know, it's a part of household today. Amazon Cloud, Google Cloud, Microsoft Cloud. So anything that's being processed somewhere in the data center with powerful GPUs or CPUs, that is cloud. And the leaf node of that is called edge. Leaf node of the network is edge. It could be your cell phone, it could be some other device, let's say your thermostat or a doorbell, say Ring or Nest. So those are edge devices. They're connected to the internet, right? And machine learning, essentially, we will use model training and inference, and I'll elaborate that a bit if you are not familiar with that. The benefits of TinyML are quite a few, and the three that comes across very loud and clear to most people is low power, low latency, and security, and that also we will cover in the next slide. So what do you do? What do we do when we would like to sort of bring ML app or develop a machine learning application to run on a tiny device, right? Like a cell phone or a microcontroller. The entire flow is where you start to gather the data. If nobody has tackled the problem, likely there is no data set. So the first thing you would do is to start collecting the data set. And you look at the data set like a data scientist would do. You see if it's enough for your problem and the solution building, and also cleanse the data set. Like, have you had enough variations of that data so that the model that you're training or the network you're training can generalize enough. So once you're done with the gathering data piece, you design your network or an algorithm. If it's not a deep learning, then you will have some kind of a machine learning algorithm that would consume this data and would iterate to train your model, right? And that's the next step. So you train the model, tune several hyperparameters, and go through this loop. If the accuracy of training and test set is good enough, then you go and look at the validation. So if the validation accuracy is good enough and you are satisfied that model has generalized well, then you go to the next step of compiling the model. And that is a crucial step where there's a lot of gap. And if you want to run that in the data centers today, there are a lot of businesses who are offering that, close to 5,000 in the United States alone. But the data goes to the cloud and processing happens there and comes back. So the bandwidth and rest of the infrastructure that is needed, you need to adopt that, and that makes the entire solution complex in the field. And there are areas where you don't want that complexity. So what you want is you want to compile the model on the target device without any requirement for the connectivity, and that's where TinyML comes in, right? It's an optional connectivity. You can have the model or the output of the model go to the cloud for history sake or some other analytic building purposes sake, but it's not a requirement. And then once you have the model, you design the application. So that is those are the 6 steps essentially that most people would adopt if they were to bring or develop a TinyML application on a tiny device. So how different is it from typical machine learning, right? So what is TinyML? Why is there such an initiative of TinyML? Why can't we consume it in the machine learning itself? There are quite a few things that actually differentiates this TinyML initiative from rest of the machine learning. So number one, the focus is low power machine learning, meaning, and I'll show in the next slide that power is the major driver or unnecessary byproduct of training these models and running them in the data centers. And so the carbon footprint that results out of those is not desirable. And TinyML is also running the system on an embedded system, running the whole process and running the whole application on an embedded system with a few kilobytes and several megahertz of a basic CPU, right? And with optional cloud connectivity. It doesn't have to be connected unless you want it connected. And these edge devices, these tiny devices, are anywhere within $10 to $60-70 range. So very affordable per device. If you want to create something for you, your family, or your university, it should not take more than a few $1,000s at scale. And if you want to scale it for the rest of the world, start a company, then the cost comes down even further, right? And of course, very important for me is privacy and low latency. Right? There are cases where you can't afford privacy violation, and we'll talk about some of those. So this is exploring in several edge markets and verticals. On the commercial side, there are several pillars that are pushing machine learning to the edge. And if you take vision AI, right, that depends on image sensors. And it's interesting to note that in 2020 alone, this year alone, there are about over 8 billion image sensors that are being produced. And so the graph you see on the top right is comparison of world population to image sensors. So this is 2020 right here, and the total number of image sensors that are produced is more than human population. Now, why is that comparison interesting? And the reason is that each one of us, if you assume the life of an image sensor to be about 3 years, each one of us are carrying 3 image sensors on average. And the bandwidth requirement out of that, if you were to put all the data from these sensors to the cloud, is about 100 exabytes per second. Let me repeat. 100 exabytes, and that is 10 to power 20 bytes per second. And so to support that, you need 10 to power 20 bytes per second. But what we have available today is somewhere between 50 to 100 gigabytes per second. So the comparison of what is required versus what we have is different by the order of 11. So 10 to power 11, sorry, by the order of 9 or 10. So it's a large number, which, if we continue to advance the bandwidth, you know, that we've been in the last 10 years, it'll take us another 20, 25 years to reach to the level where we can support the data to transport to the cloud entirely. But in the meantime, one thing comes across very clearly, that the data that is captured on these devices from image sensors must be processed because there is not enough bandwidth. And it must be processed on the edge. And if you are doing something related to vision AI, that means the model must work on the edge device itself and reduce it by a factor of, by the order of 6 to 10, so that it does not require bandwidth for, it does not explode in terms of the data and the bandwidth requirements, right? And that is possible by running these complex models on the edge. And that's one of the technical reasons for vision AI. Now, there are several, right? For example, NLP, natural language processing, where you, talk, and some of the smart speakers will make sense of what you're saying and respond to your speeches and commands. For example, hey Alexa, hey Siri, or hey Google. And the system wakes up and then it's listening to the rest of the speech. So there are two components to that: wake word detection, where the word is being listened to every second, and that algorithm is very low power, running in milliwatts. And essentially what you have is a DSP inside, digital signal processor, which is very, very efficient in executing some of these FFT and STFT kind of algorithms, FFT for fast Fourier transform and short time Fourier transform. And those are running under few milliwatts on a DSP. So they can run for years just listening to you. And so that is the advantage. Once the wake word has been detected, then it wakes up rest of the system to process your series of commands. And that model, that wake word model, is very tiny. So Google has that model under 13 kilobytes. We have slightly smaller version of that in 12 kilobytes running on our server, which I would take you through in a minute. But the point here is that not everything requires the use of cloud or GPUs and TPUs and NPUs as the media and some of these businesses would have you believe. Most of these beautiful algorithms can be miniaturized enough so that they can run on these tiny devices. And so there are quite a few, right? I would go through each one of them and I can spend 10 minutes on each, and that would eat up my time. So let me take up the biometric as the last one. So let's say if you have a device that is collecting either you're some kind of a biometric information, iris of your eye or a fingerprint, for example. Fingerprint typically is collected under 129 points. So you might have gone to a 24, a gym or a club, or even your cell phone has a fingerprint sensor behind it, right? What it does is it stores, it captures 129 points off of your finger right here. And then it matches. And if that processing were to happen on the cloud, where you're sending these 129 points off to the cloud, once that information is compromised, you will have to lose your finger, or not use it in the biometric identification anymore because somebody else has that information. It's been hacked. So it is so important to not send the biometric information for the sake of privacy and also your own personal security and safety, that information be processed in the edge device itself. Um, so I think I've made my case that there are a lot of reasons, technical and socio-economic reasons, that AI and ML processing is being pushed to the edge, supported by a lot of data, facts, figures, markets, and verticals. So let's look at the hardware, right? So far, GPUs that are in practice, they support more than terabytes of flops. Flops is floating point operations per second, and typically a unit where we measure how powerful his hardware is. And so GPUs support 10 to the power 12 with many boards running in gigahertz and spatial architecture with spatial fabric for the parallel connections to onboard the data from the disk to RAM to the GPU board itself. And they run from several tens of gigabytes to hundreds of gigabytes of RAM. And one inference and training can take up to 455 pounds of carbon emission. So a large amount. The second level is your CPU, mobile and laptop. And their flops goes down by an order of 3. So they are giving 10 to the power 9 or several gigabytes of flops with multi-core gigahertz. And they can be as basic as 4 gigabytes, but then they can go up to typically 32 to 64 gigabytes as well. And running your training on those will take about 45 pounds of carbon emission. And if you do the same thing for tiny machines, MCUs, like the one you see in my hand. So this is an MCU with 40 megahertz of ARM Cortex M4 and 256 kilobytes of memory, and close to 10 sensors on this board. And that is giving us about millions of flops with one or dual core, sometimes a DSP, up to 256 kilobytes of RAM. And if you happen to train, that would emit about 10 pounds of carbon emission. So socio-economic factors, if you look at from the environment standpoint also, these tiny devices are very friendly for the environment. And so this slide talks about as how the power goes up as the applications you see, right? On one close to origin is your applications that are running in microcontrollers from few milliwatts to under a watt. And TinyML is, the boundary is still being debated as to where the TinyML initiative is, because it's intensely focused on low power devices. So this graph gives you a visual representation. On the x-axis, you have increasing power and cost of the silicon and the board. On the y-axis, you have floating point ops per second in the increasing direction. So microcontrollers, or the TinyML movement, is essentially focused on applications that can be brought and processed on these microcontrollers from 1 milliwatt to up to a watt. And practically everything can fit in that range, including object detection. At the expense of your precision, maybe a bit of accuracy, it can run on these tiny devices. It may not give you 99%, it might give you 94%, but in some cases, you don't need 94%. You don't need, for example, very high performance. To give you an example, autonomous vehicles, for example, what Tesla has, they have a board that can process up to 20,000 frames per second from their 6 cameras. They're getting rid of LiDAR at this point. To make sense of the information around us, they have 6 cameras, and the board does process about 20,000 frames per second. Compare that to another application where you would like to find out if the door is open or closed in the night. You want to make sure that the door stays closed, let's say from 9 p.m. to 6 a.m. so that intruder does not get in. And if it is open, you sound the alarm. That application can be run under a watt, and it's good enough for a microcontroller to run with, because you don't need 20,000 frames per second. You can have 1 frame per second. It's hard for somebody to open the door, get in, and close the door within a second. So 1 frame or maybe 5 frames per second is good enough for that kind of application. So it depends on the application as to what kind of performance do you want, and performance will drive your power number as well. And there are quite a few applications in vision, which is most power hungry, that can be brought onto these tiny microcontrollers. I haven't heard any questions. You guys, I think either it is crystal clear, or I'm giving you a good sleep. Either way. So let me know if you have any curiosity or questions. So let me move on to a couple of applications, right? So this is an application, I Speak, which we developed in collaboration with a large MCU vendor. And the person on the screen is saying thank you for listening to my lecture. Uh, so this is gesture to speech technology, and the technology behind this is essentially this is an app with 5 different steps, and it runs actually on the same board that I showed you guys. It is about $20, $25 board that you can purchase, and it has an IMU, inertial measurement unit, with accelerometer and gyroscope. So we trained our network off of the data from accelerometer and gyroscope, IMU unit essentially from this board. And the idea is that the IMUs can sit on your fingertips like you have 10. And the data that is being gathered from these sensors is brought to a central unit, and then put through this neural network. So when you're signing, for example, this is hello, this is how are you, and when I'm moving my hands, the sensors are collecting this data. And this data in real time is put to a simple processor with these 3 layers, just JAM, which is essentially your general matrix multiplier, generic matrix multiplier, which is W times X plus B if you know weights and biases in the machine learning. So 3 layers of JAM and ReLU is enough for the neural network to decode up to 10 words. And if you multiply and make it 10, then the possibility increases manifold. You can decode more than 5,000 words, which is practically spoken language for most of us, with enough vocab that we can carry out 99% of our work. So after that is processed, then you might want to put it through you actually have top 5 word predictions, the probability of the gesture being one of the words. So you take those top 5, and maybe you throw in another NLP algorithm for next word predictor, combine these two to find what is the best possible guess for the word. Once you've decoded that word, it's a matter of putting that word through a speaker. And when I'm moving my hands, and signing to other person in real time, you can convert that to a spoken language. And imagine what that would do to 70 million mute population globally. That's a large number. And if we can unlock our disability, which is not being able to speak to mute population, it would unlock the joyous conversations and wonderful ideas that can take place between mute population and rest of the world, which is about 7.7 billion today. And that in itself, being able to achieve that is a magic. And this is what I call the magic and the excitement on a daily basis. The kind of application that can be enabled on TinyML are enormous, and they excite me on a daily basis. So what I'm going to do is I'm going to take you through the software that and show you how you can use the platform to develop applications like that, and what is the ease that exists today, and how does it help you. So if you don't have the account on this tinyml.studio. You can fill in the information, get an account. This is free for everybody. And let me log in. And once I log in, I would have this gallery. And this is what I'm talking about, sign language sensor app. So, and this is exactly what we have put into this device for. And this is a prototype for a couple of words, but we have experimented with more words and it works beautifully. And this is essentially the notebook that outlines the process that we trained this whole thing on. I'm not going to go through because of the limited time, but what it is essentially you set it up and then you upload the data that you collected for training from this. So what we did was we held this device with in two fingers, and then we started signing like this, probably 50 times for each sign. And we also had help from some of the mute friends that know sign language way better than I do. So for this prototype, for this POC, what we have is a couple of files that are collected as hi and what's up signs. And the data set is loaded. You create the graph, and then you train the neural network and build the model essentially. Train it, evaluate, verify, save, and then compile. The same steps that I went through with you guys a moment ago, right? So these are the same steps, the same 6 steps that I outlined in the slide. If you are curious as to how can you take and extend this to the next level, please come drop me an email. Professor Shi has my email. We will love to help you out if you are excited by this or any other application, right? So this is one application which is for the greater good. I mean, if somebody comes and takes this and creates a company, you have 70 million customers waiting for you, right? So it just needs to be brought to a point where it can be put into the production. It's a fine idea. The other application I'm going to take you through is a wake word detection. So when you, so most of us have either, a cell phone. So when you say, hey Siri, so cell phone like this, when I say, hey Google, my Google wakes up on the screen, right? So what is going on, what's happening on that device when you say wake word? So these are the things that, these are the steps that, are used in creating that application. So the mic is always on, and there's a simple algorithm that's running in milliwatts that's looking for that hot word, and every second they are capturing this audio, and that is as low as 16 kilobytes of sampling, and then they put through that to a DSP, likely running a STFT algorithm of some kind, a fast FFT, short time Fourier transform, which converts the sample into a spectrogram. And that spectrogram is put through a wake word detection ML model, and that tells you and gives you the probability whether the word was spoken with 90% or higher probability or less than that. And so you decide a boundary, and then you generate a signal so that rest of the device wakes up and is ready for the commands. And that happens within a matter of milliseconds. So that's how this whole machinery works. And the network that we used for that purpose on our platform is, the same board has a microphone as well. So we use the same board for this POC, and here is a URL on top, and this is in the references too, in case you want to play around with that. So what we did, we trained this and compiled it onto the device. And let me take you to that application quickly. So while this is taking some time, let me go back to let me take you to another feature that you might want to use. So this upload is essentially connected to sensors. And what you can do is currently you can record your voice on the platform itself. It could be either audio or your video. This is a video feed. You can start recording, you can pause, resume, and stop, and same thing with the audio. In the wake word detection example, we are actually training the word that you will have to speak probably 50 to 100 times. And that becomes your data set. And it's as easy as that. Create a file. For example, let me start. And this has started recording my voice. Probably not because Zoom has captured my mic and this won't work now. But you can play it around. The idea is for you to create the data set by speaking the words instead of, hey, Google. You might want to say, hey, Thomas, or hey, Rohit, if you like me, and create an application with my name on it. And every time you take my name, that device wakes up or maybe possibly calls my number or something. Just kidding. So that's the idea. You can save that as a data set and bring it to the wake word detection app, which is right here. And all you have to do is to replace the file that it is using, for example, wake word data set, to your file that you just recorded. So it takes three different files. One is your background, meaning if I'm not speaking, what is the noise behind me? That. Number two is your hot word. Say, hey, Rohit, 50 times, and that is your hot word data set. And the third one is the negative data set. Like, you read a page of any unrelated book that does not have my name in it. And so these three files you record and give it to this application, and this would do the work beautifully and give you the model at the end. And it does all kind of analysis. You can see how your how your spectrogram looks like. You can also test and see some of these, the audio files that are recorded, and also test on the silence. And this actually plots where the machine is able to detect the words that are being said. And that is on the basis of your integration. So essentially, it looks at the probabilities every milliseconds, and it finds out half the word matched or the entire word matched. This is just another algorithm that you can use, or you can use your own to find the boundary when the word was detected. And the only thing left is to compile it to the MCUs, and it's as simple as that. Or you can use the compiler on the TinyML Studio that is integrated already. So that's that. Any questions? I'm going to take a break here if you guys are still listening and have a question.
Hi, Mr. Sharma. So my wife actually has a degree in deaf studies, so she knows ASL well. So that was a very interesting topic to me. How do you manage, because ASL has a topic, comment, grammar structure, how do you manage the grammatical translation from ASL to English?
Right. So that's where NLP comes in, right? I mean, so there are certain words that would be decoded as words. Now, how does it make into a sentence is essentially where the NLP takes over. It would detect and create the correct sentence. Just like if you would search in a Google and it gives you the next three words that you would want to search based on the data set it has, and that's also a similar algorithm. That is the idea. We have played around a little bit in POC. By no means it's a production worthy algorithm, and that's where some of the research comes in as to what fits to make it to take it to the next level or not. But I agree with you. It's not to scale it to 1,000 words or so. You will run into a lot of other issues that we haven't seen. right? And this seems like one of those. But thank you. Very good question, Brian.
Thank you.
Okay, so and then there are other use cases, right? For example, robot-assisted surgery that has a microcontroller. Neuralink is working on a microcontroller that is running some kind of a model that today can actually map based on the ECG, actually EKG waveforms off of a pig uh, to detect, to predict the movement a few milliseconds before, as to which direction is it going to, what is the frame of the skeleton frame going to look like. They actually demonstrated that about a month ago with Elon Musk in the conference. So that is working, and that's also a microcontroller and part of TinyML movement. So the idea here is to sort of leave you guys with a bit of excitement as to what is possible. And if you have ideas like that, either you can work on your own, or we would love to help you out with that too. So why did we start? What does the current development process looks like, right? So this dude who's sitting on the left is a data scientist working with GPUs and TPUs, and that model we are hoping to bring to a tiny device that you can hold in your hand. And that is the challenge. Now, there are a lot of challenges. For example, the skill set that you need ranges from data scientist to an embedded developer, which is hard to find. The second one is ever evolving AI, models, which are complex. Number three is missing software stack, and that is our forte, which we are working on. And also the missing modules in microcontrollers that are required to create a reasonable application, right? So that is also evolving. So there are a lot of challenges in the current development process that requires to, almost a company of 5 different skill sets in the engineering team itself to take the idea to working prototype. And this is what it looks like. You set up your software and hardware, acquire the data, train the model, analyze, develop app, compile app, flash app, and monitor device. And then that requires the skill set from, let's say, hardware engineer, a data scientist, a software engineer, embedded developer, an IoT engineer to know some of the details, right? And so we are hoping to create a stack that automates most of these steps with the compiler sitting in the middle and giving you the best value for bringing a complex AI model onto a tiny device. And it's as simple as connecting your device to a laptop and taking it to Canvas, which is our platform. It's an end-to-end platform. You don't need any setup. Just log in and you have everything working immediately. If you are used to using TensorFlow and some of the other frameworks like PyTorch, we support that as well. We offer cross compilation in the software, in the platform itself. You just have to pick the board and the type of processor, and then we will give you a binary that runs. We also have pre-compiled models, and best of all, it is free, right? Some of the applications. So the philosophy that we are adopting for the platform is no code, low code, and full code. And what that means is if you don't have time or don't want to code, you can bring the model that is available in the open source, and we will give you the binary that runs on your device. It might be limited in functionality. And low code meaning if you want to adopt, for example, wake word detection, instead of saying, hey, Alexa, you want to say, hey, Thomas, or hey, Brian, right? You record your data set and then train the model, and we'll let you download the binary. So there is a little bit of a coding skill that's needed as to how do you record the data set and plug it into the notebook that we have already. And then of course full code. And for full code, we do provide all kind of features, including Python notebooks in the server in the TinyML Studio. and also C++ notebooks that you can compile right there and download the binary. So some of the features I'm not going to go through again. This is where the magic comes in. Anything you put a smart in front of essentially is becomes the user of TinyML Studio initiative, either a customer, a partner, or a user. And there are unlimited number of markets and verticals that it's going to disrupt in next 5 years. So if you have not thought about TinyML, think about it. And especially at a higher level, if you are going to stay in the software, make sure you have few courses covered in machine learning. Like it or not, machine learning would become part of software 2.0 in next 5 years. Either you will be using some kind of model, you will be developing, or you will be deploying. So you have to know basics of machine learning, if not in TinyML, in software overall. So make sure you have some of those skills before you enter the workforce. So what do we have inside the platform? TinyML tools, right? We support all kind of frameworks, including our competition, TensorFlow, PyTorch, Keras, Onyx, and even Python. You can take that, compile that. We provide a vendor-independent library, and if you have a vendor that has a library, we integrate that too. We can give you a WebAssembly code, C++ code, or a binary, or a dynamic executable, or dynamic linked library, a DLL, or an executable. Currently, we are much better than the alternate, which is TF Lite Micro. Better on pcram comparison, as good or better on CPU time, much better on low power, much better on code size, and so on. And so I'm running out of time, so I'm going to cruise through some of these algorithms that are being used in our framework. So if you are familiar with Vision AI, generally these networks, they have some unnecessary layers that are only useful for training. Pruning requires that we drop out, we remove those layers because they're just a placeholder for inference. So that is essentially your pruning. So prune out the layers if they're not needed. It definitely improves your performance. And few hardware vendors would provide combined version of few layers like conv, maxpool, or reloop combined into one to improve pcram efficiency and CPU efficiency. So we use that, and you can combine these into one operator, and compiler will take care of that given the hardware you have, right? So that's called fusion, and then of course splitting some of the algorithms. For example, if you have an addition of two matrices that you can easily think of in terms of splitting that large matrix into 4 different matrices with 1/4 of pcram requirement, and that is the advantage. Now, if you're working on a cloud data center machine, they don't have that limitation. So we are focused on reducing the memory footprint and code size. So some of these non-intuitive and intuitive algorithms, they come in handy. And again, if you have excitement, curiosity, and you like challenges, and have a problem that needs solving, nobody has looked at that so far, please do drop me an email. We have smart set of engineers and a team that is driving another program called Canvas Scholar. Currently, it has enrolled about 250 students from world over. So they can help you out, and if it is exciting enough, maybe I would donate some of my time for free. Again, try it out, see where that good takes you, and make the world a better place. So these are some of the resources that I would send to Professor Shi. And it talks about the papers for keyword spotting and wake word detection and some of those. With that, I hope I have been able to give you some food for thought for your next selection of coursework and papers. And this is my time, 9:20. Thank you, guys.